The Newton-Raphson method is another numerical method to allow us to find roots to equations. The formula for it is on the screen there. You are given this formula in your formula booklet, but it's probably worth you copying it down now because you're going to be using it for next lesson. So let's see what this formula is actually telling us and how it helps us to find roots of equations. So I have got a general function f of x there, and I'm interested in finding its root. What's the x value there? That's what I'm interested in. Now, what I've done is I've just picked a completely random point, x0. This is my first guess at what the root is. And as you can see at the moment, I am way away from what it should be. This first approximation is rubbish. It's nowhere near that. But what I'm going to do is at the point where x equals 0, I'm going to draw a tangent. At point x0, sorry, not when x equals 0, at the point x0. I'm going to draw a tangent. And I'm going to find where that tangent intersects with the x-axis. That's going to, so the x coordinate here, that's going to be my second approximation. And as you can see, that is a little bit better as an approximation from a root. It's closer to the answer, but it is still not very good. The first approximation was quite far away from the answer. This approximation is a little bit closer, but still not great. So I'm going to now repeat that process. I am going to draw a tangent at x1 here. So that tangent intersects the x-axis here at x2. And you can see that that is now starting to get to be a pretty good approximation for that root. It's not too far away here. The first approximation was this far away from the root, really bad. The second approximation was this far away. Bit better, but still pretty bad. The third approximation, x2, you can see is pretty close now. And I could repeat the process again if I wanted to. I could draw another tangent at x2 here. And let's find out where that tangent intersects. The x-axis, well, that tangent seems to, x3 seems to be almost exactly the root that I wanted to find. So by drawing successive tangents and seeing where they intersect on the x-axis, that gives me successive approximations for the root. And that's what this formula does. If you're interested in me deriving this formula for you, there is another video in the playlist that I'll link in the description where I derive this formula. But basically what that is doing is it's saying we start with a value x0, and then to get x1, I do x0 minus the answer I get where I substitute x0 into the function, and I divide it by when I substitute x0 into the gradient function. By doing that, that is the process of me drawing a tangent and finding where that tangent intersects on the x-axis. And then to get the next approximation, I draw a tangent at x1 and then find out where that tangent intersects on the x-axis again to give me my approximation for x2. Excuse me. And so on. Again, to get my third approximation, I draw a tangent at x2 and find out where that tangent at x2 intersects on the x-axis. So that is the formula for Newton-Raphson, and that is how it works and how it gives us a good approximation for roots. There is an issue, however. There is something to be aware of, and it's stationary points. This process will go wrong if you tried to pick a stationary point. For example, in this case here, I'm trying to find this root here. If, for example, I picked x0 to be this stationary point here, so remember what I do, I draw a tangent at that point and I find where that tangent intersects on the x-axis. But the problem is, because it's a stationary point, that tangent is parallel to the x-axis. It is never going to intersect on the x-axis. So therefore, I would never have a second approximation, and the Newton-Raphson method will fail. So that's something just to bear in mind, making sure that we pick our first approximations to be away from stationary points. Right, so let's have a look at an example. So, the diagram shows part of the curve of the equation y equals f of x, where f of x is equal to x cubed plus 2x squared minus 5x minus 4. The point A with x coordinate P is a stationary point. So we have this point here, that's a stationary point there. The equation f of x has a root alpha in the interval 1.8 to 1.9. So this is alpha here, this is my root, that is between 1.8 and 1.9. Part A. Explain why x0 equals p is not suitable to use as a first approximation to alpha when applying the Newton-Raphson method. Well, this is what I've just explained previously. The fact that p is a stationary point, the fact that this is a stationary point here means that the tangent at that point will be parallel to the x-axis. Therefore, it would not intersect the x-axis again to give our x1 our second approximation. So that's my answer to part A that I've already written out there. Part B. And you can see I've already written this out, so I'll explain it. So part B says, using x0 equals 2 as a first approximation to alpha. Remember that we said that alpha is between 1.8 and 1.9. Alpha here is between 1.8 and 1.9. So we're using 2 as a first approximation to alpha. So what that is meaning is we're drawing a tangent at 2. And we're finding where that tangent intersects on the x-axis to get our second approximation. So I'm using Newton-Raphson to do this. Newton-Raphson, the formula here. Now, because I need to have the gradient function, the Newton-Raphson formula involves dividing by the gradient function. So because of that, I need to differentiate. So here is the original function, just copied out from here. And here I have differentiated it. So applying Newton-Raphson for the first time, it would be x1 equals x0 minus f of x0 divided by f dash of x0. x0 is 2, I was told that in the question. This is me substituting 2 into the f function. This is me substituting 2 into the f dash function, the gradient function. And that, if I type all that into my calculator, so 2 minus this fraction, that gives me 1.86 reoccurring. So that is my first, or rather my second approximation. If x0 equals 2 was my first approximation, then 1.86 reoccurring is my second approximation. Notice that that is between 1.8 and 1.9, so that looks to be a better approximation than the first choice of 2. Now to apply Newton-Raphson for the second time. So x2 equals x1 minus f of x1 divided by f dash of x1. So same formula, but I'm now substituting 1.86 reoccurring, the first answer. When I actually type this on my calculator, I type answer in here instead of 1.86 reoccurring, and answer here, and answer here, and answer here. But typing that into your calculator, you get a second, the third approximation, sorry, as 1.856 to 3 decimal places, and that is the answer to part B. So just to repeat one more time what I've done there, my first approximation was 2. I was told to use that in the question. I substitute that into the formula. To use the formula, I had to have the original function and the gradient function, so I needed to do a little bit of differentiation. This is me substituting 2 into that rule to get my first answer. Then I substitute that answer into the rule again to get my second answer. So 2 was my first approximation, 1.86 reoccurring was my second approximation, and then 1.856 was my third approximation. There is a part C to this question, which is just confirming how good our answer is, really. Part C, by considering the change of sign in f of x over an appropriate interval, show that your answer to part B is accurate to 3 decimal places. So this is actually just a callback to what we did on sheet 1 of this topic, where we looked for sign changes in intervals. So this will allow us to prove that actually the answer is in fact 1.856 to 3 decimal places. So our suitable interval will be the upper bound and the lower bound of 1.856. The lower bound of 1.856 is 1.8555, and the upper bound of 1.856 is 1.8565. So I substitute both of those into my function to look for the change in sign that is going to imply a root, because the function will equal 0 in between those, hopefully. Substituting my lower bound into the function gives me minus 0.003. Then substituting the upper bound into the function gives me positive 0.009. And I can see that one's negative, one is positive. Therefore, and this is the sentence that we write to make sure we get all the marks, there is a sign change in the continuous function, so there must be a root in the interval where all of the numbers in that interval round to 1.856. Therefore, the answer must be 1.856 to 3 decimal places. It can't be anything else. And that just shows there the power of the Newton-Raphson method. In just 2 calculations, we have got an answer from a complete guess to begin with, a guess of 2 to begin with. We've got an answer that's actually correct to 3 decimal places, which is pretty accurate with only 2 calculations. So that's the Newton-Raphson method.